good. I'm saying we're going to learn about surface tension. I know you might have come across a concept related to this. I don't know if you can be able to define for us what surface tension is, or what you know about surface tension, or an experience that you might have had about surface tension. Is there anything you know about surface tension? Just a try. What are you saying? Yes, in senior one. What is it? So can you try to define for us what that you know, what it is? What is surface tension? I now want the definition. What is surface tension? What it is. Now, having said that, you already had a concept in senior one. Can be texting from the chat there, I will be able to read. What is it? Queen, what is surface tension from the concept you got in senior one? Is the force acting on a liquid surface that makes the liquid surface behave like an elastic skin. Great, great. Force acting on a liquid surface, force acting on a liquid surface, making it behave like a stretched elastic skin, making it behave like stretched elastic skin. Very good. There you get it correct. This is actually a case where you realize that when you try to put something on the surface of a liquid, sometimes this thing might be even, the density of the object might be higher than that of the liquid, but it does not sink. It remains floating on the surface of a liquid. Why does it remain floating on the surface of a liquid? You find it is because there is a force which is acting on the liquid surface. And this force makes it to behave like a stretched elastic skin. When you try to actually stretch your skin, you realize there that this skin it is what stretched. When it is elastic. When you stretching it, it is elastic. When you stretch it like this, it is elastic. So it can't be able to what? When you stretch it, it is elastic. It comes and goes back. So the liquid surface tries to behave like that. It is simply because of that force that acts on the surface of the liquid. Alternatively, you can be able to define surface tension as the force per unit length, you can say it is the force length force per unit length acting normally. I hope you're seeing my sorry about this. Acting normally force per unit length acting normally along a liquid surface, along a liquid surface. So you can see alternative way of trying to define this. It is the force per unit length. The force is what? Per unit length. And it acts normally. Normally means perpendicular. It acts at right angles to the surface of the liquid. So that force is now said to be called the surface tension. Actually, this definition that I've given here, it is more scientific than the one that you've given, but the other one is a little bit simplified because you're trying to say which one is more correct. Both are actually correct, but this is better one that I may say you have to take it. It is the force per unit length acting normally across or along the liquid surface. So it acts at right angles to the surface of the liquid. Sometimes what next they might ask you to do is describing an experiment to verify. You might be asked to describe an experiment to verify surface tension. You might be asked to describe an experiment to verify surface tension. So what do we do? What do you do in order to describe an experiment? What procedure do you follow here in order to come up with the steps? So this can be the question. Describe an experiment to verify surface tension. I'll be following you closely from the chat. What do we need in order to describe this experiment? What are the things that you need in order to determine this experiment? So that you can be at the end. In physics, as you try to describe an experiment, we usually say the clean water is poured in a beaker and allowed it to settle. That's what you're saying from the chart. Clean water poured in. I want to transfer this one straight away here. Clean water. So the procedure for this is you're saying clean water is poured. Clean water is poured. Clean water is poured in a beaker and allowed to settle. Allowed to settle. That is correct. Next. Next, just repeat what I've said with the needle. Next step. Said a needle is careful what? Could you just have a repeat of what You have just given me the next step. After clean water being poured in a beaker and it has settled, if I can just get to the chart, saying a needle on a blotting paper is gently placed on the water surface, correct? So a needle on blotting paper, a needle on the blotting paper is carefully put on the liquid surface correct? That is true. And then your next step is after some time the paper sinks, leaving the. Now that comes to the observation. You are there now going straight to the observation. Actually, this describes now the experiment. Then we shall move to your observation. What you've come up with there is now the observation. See, what will be the observation? So eventually, after all of that, you needed to leave the experiment. I mean, after that, you need to leave the whole thing to settle for some time. So after some time, and now what you've said there will happen. You point here that where you're saying after some time, the paper sinks, leaving the needle floating on top of the water. That is correct. Why does the paper sink after some time? Before the paper sink, and what happens? It is a correct observation to that, but before the paper sinks, something must have happened. What has happened before the sinking of the paper? Queen, what? Due to capillarity, good trial. How could you explain, or could you tell me how it happens? The right there is after some time. You see, after some time, what happens is that after some time, what will happen is this blotting paper will absorb water. Blotting paper will absorb water, and then after it absorbs water, it gets wet, absorbs water. As it absorbs water, so it gets wet, eventually sinking, making it to sink. So after it sinks, in fact, after it gets wet, as a result of absorbing water, it now sinks. So you're saying the paper absorbs water and sinks, correct? So then after this, it now leaves the pin floating on the surface of the liquid. So what comes first is this: the paper absorbs water. Then after absorbing water, it now sinks, leaving the needle floating on the top or on the surface of the water. But the correct language here is the surface instead of saying the top. The correct scientific word here is the surface, leaving the pin floating on the surface of the water. Actually, so that is the scientific, that is how we can be able to describe the experiment. If I can just go back to, we can get back to here. So if we are to describe the experiment, so the procedure is, I was saying a clean water is poured in a beaker and allowed to settle. After this, a needle on a blotting paper is carefully put on the liquid surface. The language is carefully put, not just anyhow. Don't throw. If you throw, it is not going to be right. It has to be carefully put on the surface of the liquid. After it has been carefully put on the surface of the liquid, you will now move on to the observation. You now move on to your observation, where you have to wait for some time. So what happens, what will happen after some time? That's what we were saying. After some time, it will be the floating paper absorbs water and sinks, leaving the pin floating on the surface of the liquid. What other, instead of, if you don't have a blotting paper, in that case, what can you use? What is the other option to a blotting paper if you don't want to use blotting paper? What is that option that you can have instead of blotting paper? If you don't want to use blotting paper, if you don't want to use a blotting paper, Sheila, you're welcome. You can be using a filter paper. You know what is usually available at every time in the laboratory is the filter paper. So if you don't want, if the filter paper is not the, if the blotting paper is not there, so you can go for filter paper. Filter paper is readily available in our laboratories. Always, every time you go and try to carry out an experiment in the laboratory, you find there's a filter paper. So instead of the blotting paper, we shall be using the filter paper. Is that okay? So now, another question may be, using the molecular theory, explain the cause of surface tension. Now they can say, using, let me just say, using the molecular theory, using molecular theory, explain the cause of surface tension. Sela, I hope you're seeing my screen. Sela,
yes.
Good. So we are now here. This is how far we have moved with the concept of surface tension. We started it by looking at the definition, and now we have looked at describing an experiment to verify or to show the existence of surface tension. And we are now down here trying to use the concept of molecular theory to explain the cause of surface tension. From the molecular theory of particles, we understand that every substance is made out of small particles. From the molecular theory, we said every particle is comprises of small particles. So if we're to use this theory in order to explain the cause of surface tension, we shall be saying that surface tension actually arises from the attractive force between molecules. It arises from this attractive force between molecules. We have, if I may take you to just what we have from the site, can you can allow me to share my screen. I try to show for you what we have from the site. Well, there we go. I think all of you are able to see my screen. Sheila, you can confirm because your audio is okay. Are you seeing my screen? Sheila?
Yes.
Good. So that is how we can be able to, that's how we're able to define surface tension. This is all that we have looked at. You can say an experiment in which we're trying to show that there's the existence of surface tension. We're trying to indicate where the force is. We say surface tension is a force. There's a needle which is at the surface of the water. This water is maybe probably in a beaker or a dish. So the dish is filled with water and the needle on a small piece of blotting paper placed on the water surface. You can see we're talking about blotting paper or what? Just the, if not a blotting paper, the filter. Then thin piece of the paper shocks. Shocking means that it absorbs water and then it gets wet. Is that okay? When we say it shocks, meaning that it absorbs water and it gets wet, and then later sinks, leaving the needle or the pin. Sometimes in a laboratory station, we use pin. Those optical pins that we have, the light, the small ones even, we can use them, it works. So floating on the surface of the water, and that shows the surface tension. And then if you can, as you'll be going through these notes from the site, you have that there's a video there that you can be able to watch. It elaborates more on the concept of surface tension. So now we are saying here the water surface behaves like a stretched elastic skin. So we're now coming to the other question of asking why. I'm using the molecular theory to explain the cause of surface tension. You can see now here we have this. I hope you're seeing my screen. Please, I hope my screen is still okay. Is it visible to you all? Queen, are you seeing my screen? Is it clear? Sheila?
Teacher, it is clear. Eh? No. It was.
Now it can't be seen?
Yes.
Maybe I just allow me to share this again. Allow me to share my screen again. Maybe you'll confirm. I think you can confirm that. Is it visible now?
Yeah, go.
Is it visible now?
Yes.
Okay. So are you seeing this? Things are trying to explain for us, are trying to show the position of what? The particles of the liquid. So you can see the particles of the liquid, which at these various positions are kept by some intermolecular forces of attraction that exist in between the molecules. You find in the liquid molecules which are in the space of B at the surface only exhibit or only have attractive forces from the, like the B in the middle has only attractive force from the middle. Meanwhile, from the sides, there is no attractive force that it has from the sides. From the surface, not surface, but from upwards. It has some attractive force from the left, and then it exists. It has also some attractive force from the right, and also down to the surface of, down the surface of the liquid. So meanwhile, when you come to the liquid, like also that one in the positions of where we have A's, you can see these arrows are actually trying to show where the attractive forces are from. So usually now for the surface so tends to surface tension actually arises from the attractive force tends to arise from the molecules. So the molecules which are in the body of the liquid are attracted equally in all directions by other molecules. Centrally, we can say, for example, that liquid particle A, which is at the center of it all, it has the attractive force from all the directions, makes this on them at that point to are only attracted by molecules downwards and sidewards, just as you can see there. From the surface, the attractive force is from downwards and sidewards. So this stretches the surface molecules and puts them in a state of tension. It puts them in a state of tension. And then that tension, we now say it is a force. And then now, because we say that tension is a force, and that force, we now describe it as what? Surface tension. Is that okay? That is what we do have for this. So even if we can see from the explanation here, we're saying the molecules in the interior of the liquid air experience equal forces from neighbor molecules from actual all directions, but those on the surface B only experience forces from molecules lower than them and on the sides. As a result, they now experience a net downward force. Hence, the surface tends to contract to acquire a state of tension. So that is exactly what happens. Now the question is, how can we be able to, the question is, how do we reduce surface tension? Surface tension, how do we reduce it? Sheila, can you read for us what is on the board?
Adding a detergent.
Can you give him an example of a detergent?
Ariel.
Good. Next.
Increase in temperature.
Increase in the temperature. So those are those are just the two most prominent ways of trying to reduce surface tension. So in each of these cases, it increases the force of attraction in the molecules. In each of these cases, the increase in the forces of attraction in the molecules gets reduced. So as a result, you now find the forces here, when the forces of attraction between these molecules, when it gets reduced, eventually it's going to result into actually weakening of those forces. So when the forces get weakened, the last thing the least thing you expect is these molecules, when now the force of attraction between them is weakened, when it is broken, so there's going to be sinking. When the force of attraction between the molecules is broken, so easily whatever was put on the surface of the liquid gets shrunk into the bottom of the liquid. So that's what takes place. Now, I was just trying to say now, if this, what we were able to explain there, see, maybe a liquid is like this. I want to explain further what we had given there. You can see there's a liquid at point A, liquid molecule at point E, in the end there's a liquid molecule at point B. So what the molecular theory was saying is this liquid at point A only has that attractive force from the sides and what? Downwards. But you find a liquid which is central at point B has the attractive force which is equally in all directions. Are you seeing what I'm trying to show with the green? That attractive force exists in all the directions. So here, as a result, for this liquid at point B, so the force actually balances. For it, the net force balances. Meanwhile, for this, the net force is just what? Downwards. For it, at this point, the net force is downwards, because to the right, the force to the right is balanced by the attractive force to the left. Meanwhile, this one, which is downwards, is not balanced. When you look at the concept of forces, we said as we shall move to, I think in scene 3, have the concept of scalars and vectors, the forces. When maybe two people pull you, for example, just now you are here, see, you are here, and then another person pulls you this way. Now, in this case, if the person who pulls the force here, this is equal, this force is equal to the force which is acting in this direction, you will find that you will just be balancing at this position. You will not be moving anywhere. Your movement will be either now upwards, or your movement will be either upwards or downwards, depending on now which other force is acting in the opposite direction. If it is that now there's another force acting downwards here, because there are now those two forces, which are acting to the equal forces acting to the left and the right, then the net force, which means the direction which you will be moving, will be what? Now downwards, because there's no force that opposes or that is equal to that force acting on you downwards. So that is exactly what happens in that case during, in that case for surface tension. Now, finally, I want us to summarize with now examples or the situations in which surface tension is applied. Examples or situations or scientific evidences in which we have seen surface tension. What are the practical applications? What are the applications of surface tension? Where have you seen surface tension taking place? Where do you see the concept of surface tension being applied? Sheila, you could tell for me one, where you see that motion, or the floating of something on the surface of a liquid, where do you see that? Are you able to see my screen? Are you able to see my screen? Can you read on those applications?
Checking. Water. Form spheres as it drips, e.g. falling from a top.
Maybe if water is falling from the leaves, it forms spheres. That is an application. It is an application of surface tension, where you're actually seeing that there is strong intermolecular forces are trying to appear. But visibly, you can have an application of this in when you go to the water bodies, where some insects are able to walk on the surface of the water, even without sinking or without getting wet. Have you seen some insects on the surface of water? Have you seen some insects on the surface of water?
Yes.
Now I want you to, maybe after here, you interact on Google and try to find some of those examples of the insects that can be able to walk on the surface of water without sinking. You can see maybe your audio could unmute it. Mute your audio now. When you go to, when you try to get water, I mean, you even put water in a basin at home there, and you see when you bring what? When you actually put water in a basin at home, maybe it is under a tree. Sometimes you'll be surprised to find that some leaves have fallen onto that water, and then others are what? Floating on the surface of the water. See, it depends on as the weather. I mean, when the leaves were falling into the water, was it that when it fell on the surface, it was in a way that it got, the surface was calm and then carefully settled on the surface, or as it was falling, the water surface was a little bit disturbed, or when it fell on the water surface, the water surface got disturbed and then eventually went into the water. You realize when it gets, the water surface is calm and it falls on the water surface with minimum disturbance, you find it remains floating. And actually that is an application of the surface tension. So we have that, anyway, that video is explaining more on the concept of diffusion, which we looked at the other time. So this is what they wanted us to look at on surface tension. Maybe if there's a question. Probably from the chat, Queen is giving us the water surfaces. Very good. That is one application. Yes. Water repellent garments are covered with wax-like substances to allow cohesion in water to pull water into spherical drops. Here, as I mentioned, there further explained with the data. Here, in summary, what we're able to of surface tension, we have looked at the definition. Sheila, you're saying I'm breaking. My voice is breaking. Is it okay now? The definition of surface tension, correct? Then this was followed by the experiment. This experiment was to show surface tension. Then the molecular theory. The molecular theory on surface tension. And then applications of surface tension and how to reduce, how to minimize, or how to, it is how surface tension is reduced, how to reduce surface tension, how to reduce surface tension. So those were basically the things that we looked at in the course of our engagement here. Really, thank you for this participation. And throughout, Sheila joined us somehow in the mid of the lesson, but with Queen, we started, I think, from the start. We shall have to stop here if there are no other queries. Thanks for your active participation, Sheila. Thanks for your active attendance. Queen, that is it for now.
When will you buy me some data?
We shall have, pardon? Queen, is it Queen who's talking?
Teacher, it's me. Thank you for the lesson.
Okay, Sheila. Okay, thank you as well for attending.